Hi, welcome back. Today we're going to look at our very last chapter, which is on chapter 8. Chapter 8 will discuss on correlation and regression. In this chapter, we will look at what is correlation and what is regression. Okay, looking at correlation, what does it mean? Correlation is used to allow us to describe the relationship between two measure variables. For example, your two measure variables are height and weight, and you want to see is there any relationship between height and weight. For example, when height increase, will weight increase as well? Or will height increase, will the weight decrease? Or the other way around. The second example that is given in the lecture notes is smoking and cancer. We can also see is there any relationship between smoking and cancer. For example, will smoking leads to cancer? Correlation might vary in their magnitude. What is meant by magnitude in correlation? Magnitude of correlation is the measure of strength of the relationship. The strength or the magnitude could be no relationship, weak, moderate, or strong. And the magnitude of relationship in correlation usually is determined by correlation coefficient. And this table, which is shown in this slide, shows the size of correlation and its respective interpretation. For example, if you observe the correlation between the two variables, which range from 0.9 to 1.0, this is an indication or indicator of very high positive or perhaps negative correlation. And if your correlation range from, for instance, 0 to 0.3, this means that the correlation is negligible, or there is very weak, or there's no relationship at all. The magnitude of correlation, which is measured by correlation coefficient, could either be positive or perhaps negative. The correlation coefficient with the value of 1 is an indicator of a perfect correlation, meaning that the correlation between the two variables are very strong. Okay, we look at one example, the correlation between height and weight. Assuming the correlation coefficient between height and weight generated in an experiment, the value is positive 1.0. This means that the person with the highest weight was also the tallest person, and the person with the second highest weight was also the second tallest person, and so on down the line. In other words, if the height increase, so does the weight. Looking at the perfect negative correlation, which is with the value of correlation coefficient of -1, this means that the person with the highest weight was the shortest, or it could be interpreted as the person with the second highest weight was the second shortest, and so on. In other words, it could be interpreted as the person which is the tallest is having the lowest weight, and the opposite is also true. In performing the correlation test, usually scatterplots will be generated as well. A scatterplot, or very often we call it as the scattergram, is a figure that shows the relationship between the two variables, and it is a graphical representation of correlation coefficient. Scatterplot have four basic patterns. It could be showing positive relationship, negative relationship, no relationship, and curvilinear relationship. Okay, and this diagram shows an example of positive correlation between the two variables, the y and the x. This scatterplot, which shows positive relationship, could be interpreted as when one variable, for instance y, increases, x will increase as well. It could be also interpreted as when y decreases, x decreases as well. The y and x could represent any type of variable. Using the example that I have mentioned to you just now, the y could be height and the x could be weight. Or the other way around is true as well. Now we look at another type of scatterplot which shows negative relationship. Negative relationship scatterplot will have such outlook as what is being shown in the diagram. The relationship could be interpreted as when one variable increases, the other variable decreases, or the other way around is true as well. For example, when y increases, x decreases. The third type of scatterplot is scatterplot that does not show correlation between the two variables. For such scatterplot, the dots does not represent or show any relationship or any pattern at all. The dots just scattered randomly around the graph. The last type of scatterplot is the curvilinear scatterplot. Curvilinear scatterplot has a curvilinear relationship. The outlook of such scatterplot is as what is being shown in this diagram. It looks like a curve. For curvilinear scatterplot, the first half of this graph will show an increasing trend until it will reach a certain height where it started to slope down. This type of curvilinear relationship is usually or generally seen in the medical field. For example, between physiological arousal and performance. The physiological arousals will increase the performance until a certain level. When you reach a certain height, which is the maximum, the increment of the physiological arousals will cause the performance to go down. Or another example could be administration of drugs and performance. Usually, drugs are very effective when it is administered at the appropriate concentration. After it reaches the height or the maximum concentration, it will have negative effect, which will cause, for example, the performance to go down. Okay, now we look at Pearson's correlation coefficient. Okay, now let us turn our attention to the calculation of R value. How do we get this R value that is shown in this table? The R value that is shown in that table earlier is called the Pearson's correlation coefficient. The Pearson correlation coefficient is usually referred as Pearson's R, and this R is the statistical notation we use to report correlation coefficient. The Pearson R value of the correlation coefficient could be calculated by using this mathematical formula. An alternative formula for Pearson's R to get the correlation coefficient could be calculated by using this formula. This is a very much complicated formula which we call it as the computational formula. However, using both formula to calculate the R value is kind of tedious. So what we're going to do is that we will try to get the R value or the correlation coefficient value through by using SPSS software. We will try to do that by using one example. Okay, the question says, assuming the data represents weight and height measurements of 20 tomato plants, and you are interested to know whether the height and weight of these tomato plants are correlated. So you need to conduct a correlation analysis for the data that is shown in this table. Okay, in order to do that, first of all, you need to open the SPSS software. After that, in the data view, please enter all the data that is shown in the table of weight and height of tomatoes. And then in the variable view, label each column appropriately. I had labeled the first column as weight and the second column as height in the variable view, and then click back on data view, and now we can start to analyze. Okay, now we shall start to analyze. In order to do that, please go to analyze, choose correlate and bivariate. Click on bivariate, and this bivariate correlation dialog box should appear. Highlight weight and height and transfer them into the variable box. Next, click on Option. The bivariate correlation option dialog box should appear. Click or select means and standard deviation and click Continue. And then click OK. The Pivot Table Editor and the Pivot Table Editor menu will replace the Viewer menu. This pivot table will show the analysis result that we compute just now. Okay, now we'll try to generate the scatter plots. In order to do that, go to the menu bar, choose Graph, Legacy Dialogs, and then go to Scatter and dot, press on it. The scattered dot dialog box should appear. Click on Simple Scattered and press Define. Next, please select height and transfer it into the y-axis, and highlight weight and transfer it into the x-axis. And finally, click OK. The scatter plots should be generated. The first group statistics table shows the descriptive statistics of the analysis. In this example, the mean and standard deviation of weight and height of the 20 individual plants is shown. The last column on this group statistics table show the number of sample, which is 20. The second group statistics table is the correlation table. This correlation table shows the value of Pearson correlation coefficient, which is represented by the alphabet R, as well as the p-value or significant value. Let's try to interpret this table. The top part of the correlation table shows the value of correlation, which is correlation coefficient, which is R, between weight and height. As what you can see here, the correlation coefficient value is 0.941 and is significant at 0.001 level. So how could we interpret the correlation value that is generated? The correlation value, which is 0.94, could be interpreted as very high correlation. And now we try to see if the correlation is positive or negative. As what is being shown in this diagram, the test analysis show that the relationship between height and weight is positive. In other words, where if height increases, the weight also increases. In this instance, we are looking or comparing the height and the weight of tomato plant. We can conclude that if the tomato plant height increases, the weight will increase as well. The test analysis of correlation could be summarized in this way. Starting with the Pearson correlation coefficient, followed by the number of samples, as well as the significant value. In the example just now, we have already tested the correlation between the two subjects, which is the height and weight. And we know that these two subjects, the height is positively correlated with the weight. We can actually use the information of height to predict the value of weight. This is what we call as regression analysis. Regression analysis enables us to predict an individual score on one variable based on knowing one or more other variables. We look at one example. A school principal wants to predict how well a prospective student might do in MUET test based on Form 4 English test score. And a regression analysis could be conducted or performed in order to allow us to make such prediction by developing a regression equation. The regression equation is actually a algebra linear equation that you learn in your mathematics. The linear equation will be as what is being shown here. Y equals to mx plus c, where m is the slope of the line and c is the y-intercept. Y-intercept is the point where the line crosses the y-axis. I'm very sure that you are very familiar with this algebra linear line equation because I'm sure that you have learned it in your secondary school on mathematics. For the regression analysis, the formula is essentially the same as the algebra linear line equation. However, the symbol used differ a bit. The formula for linear regression analysis is being shown as in this slide. The symbol of slope line M is replaced with B in the linear regression, and the y-intercept, which is C, is replaced with alphabet A. The y-intercept and x-intercept basically is represented by the same alphabet, but is being capitalized. In order to get the regression line formula, we need to determine both the value of B and the value of A. Manually, B could be computed by using this mathematical equation. B is equals to R times the standard deviation of Y over the standard deviation of X. The R here is referring to the value of Pearson correlation coefficient for both height and weight. And this standard deviation is referring to the standard deviation of height over the standard deviation of the weight. After we have determined the value of B, the B which is the slope, now we must compute or get the value of A. A is equivalent to C of the algebra linear line equation, which is the intercept of Y, or y-intercept. It is calculated by the mean of the height minus the total value of B times the mean of the weight. In order to enhance our knowledge or our understanding on the usage of the regression, we try to look at one example, and using the data that is provided in this table, or which is an example, we will try to generate a regression line formula for this. In order to do that, first of all, we need to, and always remember, before we conduct any regression analysis, first of all, we need to know whether the two subjects here, or the two variables here, which is weight and height, or any variable that you are testing, have correlation, or there is relationship between the two variables that you are interested in testing. In order to do that, you must always conduct a correlation test before you perform the regression. If the correlation shows a positive or negative relationship between the two subjects, and then the next step, you could proceed with the regression to know how exactly these two subjects are related. And if the correlation that you perform does not show any relationship between the two subjects, there is no need for you to perform a regression, because the two subjects are not related at all, or does not show any particular pattern. However, in this course, we are not going to look at the generation of regression line equation using the manual or traditional method. We will use SPSS in order to help us to get the linear line equation for the regression, or we call it as the regression line formula. In order to do that, first of all, you need to go and open your SPSS software. Using the same data for weight and height for 20 tomato plants, We already performed the correlation test for this data, and we found out that these two subjects are positively related. And then now we will try to perform the regression. First of all, you need to enter in all the data into separate columns. Okay, now we'll start to analyze. First of all, go to the menu bar of SPSS, click Analyze, click Choose Regression, and click on Linear. The dialog box of Linear Regression should appear. Now, choose Height or highlight Height and transfer it into the dependent list, and choose Weight and transfer it into the independent list. Okay, next click on Statistics, and the Linear Regression Statistics dialog box should appear. The default selection will be Estimate and Model Fit. Choose or select Additional Analysis, which is the descriptive. And under the residues, choose Case-wise Diagnostic, and then click Continue. Okay, then now we choose Plots, and the Linear Regression Plots dialog box should appear. To check the regression assumption, such as normality, constant variance, plot the standard residues into the Y box and standardize predicted values. Into the X box. Under the standardized residue plots, choose or tick histogram and normality probability plot, and then click Continue and OK. Now let us interpret the test analysis result of regression. The statistical table that is generated will be model summary. Model summary will show us a few test analysis results. The first is the R, this R is known as the correlation coefficient. The correlation coefficient between weight and height is 0.941. If you refer back to the Pearson correlation coefficient that you have performed earlier, the value here is actually the same as what is being generated by the test analysis of correlation that you have performed just now. And the second most important value that is generated by the regression analysis is the R squared. The R squared, or we call it as the model variance or the total variance, tell us how does one variable account for the variation in another variable. For example, the R squared value that is generated between the subject, which is the weight and height, is 0.886. This means that the height account for 88.6% of the variation in weight. In other words, or we can interpret this data as, if the trees are taller, 88.6% of them will be heavier, but 11.4 might not be so. Okay, now we try to look at the second test analysis table, which is the ANOVA table. Okay, now we look at the second statistical table, which is generated by the regression analysis, which is the ANOVA. Yeah, regression also will generate the ANOVA table test for model significance. As what you learned in the previous chapter, the ANOVA will be used to either accept null hypothesis or reject null hypothesis. Okay, before we accept or reject the null hypothesis, we try to look at the hypothesis itself. In any of the ANOVA test analysis, two hypotheses will be postulated as what you have learned in the previous chapter. The first will be the null hypothesis, and the second will be the alternative hypothesis. Null hypothesis will always say no significant difference, and alternative hypothesis will always say there is significant difference. But for the regression, the null hypothesis will say that there is no linear relationship between the two variables. The two variables here in our example is the height and the weight. Looking at the alternative hypothesis, will always say there is significant difference. But for regression, the alternative hypothesis will be there is linear relationship between the two variables. Okay, now let us look at the very important analysis result of the ANOVA, which is the F ratio and the significant level. If you still remember, F ratio is calculated by mean of squares between over mean of square within. This is the calculation using the conventional way, or we calculate it using a formula manually. However, in this case, we don't have to calculate it manually by ourselves, and the F ratio is calculated by the SPSS software itself. Okay, let us try to interpret the test analysis of ANOVA. The F ratio that is generated here is 0.40.4, and the significant level is less than 0.05, and in this instance it is less than 0.01. This tells us that there is less than 0.1% chance that an F ratio this large will happen by chance alone. When the significant level is less than 0.005, we will reject the null hypothesis and accept the alternative hypothesis. In other words, we actually derive with conclusion that there is linear relationship between the two variables. The two variables that we are testing in our example are the height and the weight. Okay, now we look at the third statistical table that is generated by the regression analysis, which is the coefficient. There's a lot of parts of this. There's a lot of parts in this table, but I will just highlight what is important. I would like to draw your attention to this second column, which is the B value. Okay, the B, which is under the column of unstandardized coefficient, will actually give us the insight of the change of the outcome of one variable, which is associated with the unit of change of another variable. Okay, now we look at the linear regression equation in our example. In this instance, this equation is similar to the algebra linear equation that you learned in your mathematics. Y equals to mx plus c. A here is the y-intercept and B here is the slope. And how do we actually relate the test statistics of coefficient with the linear regression equation. The constant here, the b value, the constant here, which value 46.314 is representing the a value. The a value here is the y-intercept. On the other hand, the b value for weight, which is 0.141, this value is representing. Okay, now we already derived with the value of a as well as the b, and we actually already obtained the full linear regression for our test analysis. And the question you might ask, what is the usage of this linear regression equation? Okay, for example, you have the data of the weight of the plant. For instance, the weight of the plant is 200 grams, and you wanted to know or predict the height of the tomato. You can predict the height of tomato using the linear regression equation that you have generated just now. The height equals to 46.3 plus 0.14 times the weight. With the knowledge of the weight, you can actually predict the height. What you need to do is that you need to replace the unknown variable, which is the weight, into this linear regression equation, and then you try to solve the mathematical calculation, and you will derive with the answer of 74.51 centimeter. At this point, we will come to a conclusion that if the tomato plant is 200 grams, the probable height will be 74.5 centimeter, which is reasonable. Why do I say it is reasonable? You can refer back to the raw data of the height and weight that is being shown to you earlier. In the example, the weight is 200 and the height is 77. In our prediction, the weight is 200 and the height is around 75, which is almost equivalent to what is being shown by the data that is presented in this table. And so we can be confident to say that our prediction is very reasonable. And lastly, we need to look at the or reconfirm back our assumption based on two charts that is generated. The first will be the scatter plot. The scatter plot here that is generated by our data shows a random pattern or random scattered around the zero value. This confirms that the assumption of linearity and homogeneity of variance have been met. The other chart that is very important is the normal probability plot of residues generated by our data shows the dots which is scattered around the straight line. This shows that our assumption is valid. And I think that's all from me for this chapter, and this will be our very last chapter for this course, which is chapter 8. And if you have any question or if there is a necessity to conduct an online discussion, please let me know ahead of time, perhaps a week ahead, so that I could organize the webinar and we could start the discussion. If you have any question that you like to me to answer, perhaps you could either WhatsApp me, you could email me, or you can contact me through my guru, and I'll try my very best to answer it. I think that's all from me, and thank you for attention and have a nice day ahead. All the best in your future undertaking.